So,
We got a third.
let us begin. We'll continue our mad tour of non-trivial trig identities, right? So like up before your last couple classes, we had covered I would call them the trivial trig identities. These are non-trivial identities that we're discovering as we go on here, all right? So I'm going to start out with the tangent one. So tangent of a plus b. What's the identity for tangent of a plus b? So, well, what's tangent? Tangent is sine over cosine, right? And so we just write sine of a plus b over cosine of a plus b, right? Great. Now, this then, remember we learned the adding angles formula for sine and cosine last time. So we can write that as sine A cosine B plus sine B cosine A. Right? And downstairs you got cosine cosine minus sine sine with A and B respective, of course. Right? Now, that's an identity. You could just kind of leave it like that if you wanted. But there's a kind of neat way to rewrite this in terms of tangents. So what we're going to do is we're going to take this, all right, and we're going to multiply it by a fraction that makes nice things happen. So we're going to multiply it by cosine A cosine B over like this. We're going to multiply it by those so that when we multiply that through, we clear out things, right? So if you look at that, that's going to give you, I'll write it out, sine A cosine B divided by cos A cos B plus sine B cos A divided by cos A cos B, all divided by cos A cos B divided by cos A cos B plus, or rather minus, sine A sine B divided by cos A cos B. All right, it's easier for you guys to write, right? So, what happens? There's some really nice cancellations there, right? So like in the denominator, this first thing just goes to 1, right? Upstairs, you see that cosine V cancels with the cosine B, right? And let's see here. No cancellation over there. But then in the denominator, no cancellation there either, right?
Why is there no cancellation top right?
Did I miss it?
Sine B, cosine
Oh, I missed it.
A.
Thank you. Cosine A, right? Those cancel. So let's look at what we're left with. What are we left with? So we've got a sine A over cosine A, right? We've got a sine B over cosine B. And down here we've got sine A over cosine A and sine B over cosine B. Every last one of these fractions is a tangent, right? So look at what we got. We got tangent A plus tangent B divided by 1 minus tangent A tangent B. And there you go. That's the adding angles formula for tangent. All right? So, is there any particular homework question you guys would like me to work from this sum difference section? 15 on section what? 7.2, number 15. I'll give it a go. See what happens. Hopefully I don't get stuck. You never know though. see here. Number 15? Ah, okay. So section secant of pi over 2 minus theta. And what are we asked to do? What do the instructions say? This was number 15? Section, what was it? I keep forgetting. 7.2, number 15. As you guys know, we are using the OpenStax pre-calculus book. The price was right? Yeah, free. Well, mine was $25, but you know, whatever. Yeah, well, I like paper. If there's some way I can offend Al Gore, I feel like I'm doing my part. But anyway, I digress. So secant is 1 over cosine, right? So we know what to do with cosine, right? This is 1 over the cosine of pi over 2 minus theta. I suppose we're supposed to simplify this, right? It says, it says, for the following exercise, simplify the given expression. I'm sorry, I have the book. Let me stop. Okay, so we should use the addition angle formula for cosine, right? How's this go? This is 1 over, so we've got cosine pi over 2, cosine of minus theta, right? Minus the sine of pi over 2, sine of minus theta, right? So what's that give us? Remember, so you don't want to have to punch these in your calculator. Like, you need to know these instinctively, right? Like, uh-huh. Well, sine of pi, yeah, sine pi over 2 is 1, but notice that the, see that minus? So sine is odd, so we know sine of minus theta is minus sine theta. So that minus and this minus come together and give us a plus. So it looks like we got 1 over sine theta, which is also known as what? Cosecant, right? Now, we could try to understand this graphically. Maybe that would be a good exercise, actually, right? So, I mean, but the point is, with these algebraic identities, we don't have to understand them graphically, right? We can take ownership of these kinds of relations without ever so much drawing a graph. But I do think it's instructive to like see what the algebra means in terms of like a graph. See, because if we think about y equals to the secant of pi over 2 minus theta, right? So start with what's secant? What's secant look like? Well, secant is 1 over cosine, right? So secant looks like this, right? Oops, my bad. Where are the vertical asymptotes happening?
Isn't that the maximum of cosine?
Well, vertical, so this is y equals secant theta, which is 1 over cosine theta. So the vertical asymptotes are where we got division by 0, right? So those should be where cosine theta is 0. Where is cosine theta 0? Well, pi over 2, right? Minus pi over 2, etc. Minus 3 pi over 2 over here. This one's 3 pi over 2. Okay? So, by the way, y equals to the secant of theta, well, that's also equal to the secant of minus theta, because cosine's even, so you can put a minus in. That's also the graph of secant minus theta. So how about this one over here, the one we're actually looking at? How about this thing? How is that related to this graph? Well, we're taking secant of minus theta, and we're adding pi over 2 to it, right? So what does that do? that shifts the graph left pi over 2 units, right? So what happens if you shift the graph left pi over 2 units? Well, that moves the graph pi over 2 to the left. It moves the asymptotes from pi over 2 to the y-axis, right? And the asymptotes are pi distance apart, right? Because every pi you have a 0 in cosine. So you got, I'll just draw it like this, right? And the, so to the left, so this one, is that right? Wait a minute. Okay, feels wrong. I feel like I've,
If you're dealing with halves, now you're dealing with the wholes. That's why you have your 2 pies on the outside, your zeros in the middle.
yeah. What's bothering me is that's not the graph of cosecant. Oh, I'm sorry. I have to think about this more carefully. The theorem on graphing, right? It says, it doesn't just say that you add pi over 2 inside the argument. It says you take y equals f of x, and you replace it with y equals f of x minus c, right? That moves it c to the right. If it's plus, it moves it c to the left, right? So f of theta here. So I have to rewrite this in terms of minus theta. So like, I have to pull the minus outside the pi over 2, right? So secant of pi over 2 minus theta, well, that's secant of minus parentheses theta minus pi over 2. My bad. That's how I should have looked at it. So forget about the graph of secant minus theta. This is just the graph, well, curses. It is the graph. Okay, so it is the graph of secant of minus theta shifted pi over 2 to the, not to the left, but to the right. So I should have put this one here. I'll just, let me color code what's going on here. Like, I'm taking this one and moving it over here, right? And this one over here is translating to here. Wiggles for artistic purposes only. Anyway.
So what happens to that negative that you pulled out?
Which negative? Oh, well, it's necessary because, see, this is, if f of theta is equal to secant of minus theta, then f of theta minus pi over 2,
I know you have to pull it out, but where did you get your graph?
secant of minus theta minus pi over 2. So what that means is I take the graph of y equals secant minus theta, which is this, and to get that, I move pi over 2 to the right. Now you're asking what?
What does that do? Like, to that negative, it has to do something toward that graph. If I were just to leave out that negative, what would happen?
Well then, I mean, somehow I have to get the minus theta. We have a minus theta that we're trying to understand, so I have to somehow create that minus theta. I don't see another way to do it right offhand. Of course, honestly, so by the way, this is a mess, right? That is so much easier, you know? And it's partly a mess because I kind of got muddled in the middle, but also maybe not so much. But anyway, you can see this is in fact the graph of 1 over sine. Vertical asymptotes where sine is 0, namely 0, pi, minus pi, and so forth. But anyway, other homework problems you guys would like me to work through? Number 27. Tangent of pi over 3 plus x. It says simplify the expression, then graph both expressions to verify the graphs are identical. I will be skipping the graph part. Number 27. Let's see here. All right, section 7.2, number 27. We've got tangent of pi over 3 plus x. I guess I might graph it. It doesn't look too bad, actually, now that I look at it. Well, this doesn't look too bad. What I'm about to write, I don't want to graph. I don't think. Okay, so this is A, and that's B. And there's a good reason you couldn't do this problem before today, because you didn't have the tool that you needed. You would have had to gone through the derivation of this, right? Which is to use the sine identity for the top sine in the tangent and use the cosine identity for the bottom. And like, you could have done that, but we could also do this. So we've got tangent pi over 3 plus tangent x divided by 1 minus the tangent of pi over 3 tangent of x, right? So let's see here. I'm going to be lazy and just work out tangent pi over 3 with special angles because we can. You could pick up your calculator and do it if you wanted, but this is just easier for me. Root 3 over 2 divided by half, root 3. Tangent of pi over 3 is root 3. So what we got is the square root of 3 plus tangent x divided by 1 minus root 3 tangent x. And, yep. So, yep, that's it. Well, let me see if the book had something else in mind. I'll check. It is, after all, an odd problem. We can check the answers in the back of the book. Section, what was it? 7.2. I don't do well with the game of memory, by the way. Number 27.2? What the? They say cotangent. Cotangent of pi over 6 minus x. What? I'm on the odds, section 7.2. I mean, cotangent of pi over 6 minus x. Cotangent of pi over 6 minus x, they say. I mean, another way we can look at this problem, since we have their alleged answer, is, are these equal? How would we show? I mean, that's an interesting question. So let's reframe the question. Can we show that this is equal to the tangent? I think that the above is a perfectly reasonable answer given the content of the section, right? But I'm curious if this is actually true, right? So, I guess I should mention that, well, let's see here. How are well, all right, so tangent of pi over, so I'm going to try to change the tangent to a, goodness gracious. Well, a little bit at a loss here. What's the right way to think about this? Tangent of pi over 3 plus x. it may actually be helpful to go back to our derivation of the tangent idea and see where that kind of takes us. So this is really, sine pi over 3 cosine x plus the sine of x, the cosine of pi over 3, right? Divided by cosine pi over 3, cosine x minus sine pi over 3 sine x. Oh, well, goodness. There's got to be a better way to do this. But folks, I mean, this is true. The cosine of pi over 3 is the sine of pi over 6. The sine of pi over 3 is equal to the cosine of pi over 6. So we can trade our pi over 3s for the pi over 6. Yeah, so then, and that flips sine to cosine, and everywhere it happens. So we've got cosine pi over 6, cosine x, plus sine x, cosine, sine. And I'm going to do a little trick right here. I'm going to write that as sine of minus pi over 6, and I'm going to pull a minus out here. And I'm going to write this as cosine of minus pi over 6, because I know where we're going. I can do that up here because cosine's even, yeah? And so downstairs we've got sine of pi over 6, and I need to put a minus there, I think. Trying to be consistent, cosine x. And if I do that, I got to put a minus right here. And then plus the, minus the cosine of pi over 6, minus pi over 6, sine of x.
So why wouldn't they just do what we did at the beginning?
I don't know. I'm not sure why the book thinks this is. I mean, it's a neat answer, but this just goes to show you, like, simplification is in the eye of the beholder. I mean, there are many different. I mean, I guess one answer would be nobody wants to graph that, so that must not be the intent of the problem. So this requires sort of like girlfriend logic or something, Like, you're supposed to know that. Why didn't you know that? So I'm not sure I really care for it. But anyway, this is the cosine of x minus pi over 6 over minus the sine of x minus pi over 6 using the adding angles identities, which of course is equal to minus the cotangent of x minus pi over 6, right? But guess what? The cotangent is an odd function, so you can pull the minus inside. So since cotangent's odd, this gives us cotangent of pi over 6 minus x. And there you go, that's the book's answer. But, man, if I had, I don't know, like if I hadn't had that flash of inspiration that I should use that the cosine of pi over 3 is the sine of pi over 6, and the sine of pi over 3 is the cosine of pi over 6, I'm not sure how I would have seen that.
Well, I guess the question is, you have to also graph it at the end.
Oh, well, yeah, that's relatively benign.
So is that why they wanted that answer?
Yeah, I think so. That is ultimately the answer. It's because they wanted to graph that, not that. I'm nervous to ask, but any other questions? You guys, that one was kind of a doozy.
I mean, they're basically the same thing, right? Those two answers.
They are equal, yeah. You could try plugging numbers into it, you get the same thing out, interestingly. Okay, so I'm going to Listen, you guys can keep asking me more homework questions from this sections like next class. Totally fine, right? But I wanted to present some new material to you. So these are the so-called double angle formulas. Actually, we're done with this, right? Are you still, you're good? We're good? I'm going to erase. That way hopefully I don't have to move my camera. Put my camera where it's supposed to be. I had a lot of, doing lecturing calculus yesterday. I ended up writing off where my camera was. Like, oh, just had a miserable time of it. But so once you have these adding angles formulas, you can get all kinds of other goodies from them. All right, that's basically what it boils down to. And so these are some pretty famous ones. The book calls them double angle formulas. And I suppose some people call it that. But, I mean, they're fine. I'll call it what he calls it, double angle formulas. So here are his double angle formulas. He's got the sine of 2 theta is 2 sine theta cosine theta. This one's important to physics. We need to use this in the derivation of the range equation. Cosine of 2 theta. You can write this a few different ways. One way is that it's cosine squared theta minus sine squared theta. But that can be simplified to 1 minus sine squared theta. And that can be simplified to 2 cosine squared theta minus 1. So you got some flavor choices, I suppose, with the cosine 2 theta formula. Tangent of 2 theta is 2 tangent theta over 1 minus tangent squared theta. All right. And I would point out that these immediately lead us to the half angle formulas, right? Well, I don't know if these are half angle formulas, but let me just say this. The ones you need for calculus 2, notice that if we solve this one, 2 cosine squared theta minus 1, if we solve that for cosine squared, what does it give us? We get cosine squared theta is 1/2 of 1 plus cosine 2 theta. And then you can also prove that sine squared theta is 1/2 of 1 minus cosine 2 theta. So these two formulas I just wrote, these are probably or sometimes arguably more important than the adding angles formulas in terms of just knowing them. These come up in calculus later. If you don't know these, there's a wide class of problems you just can't solve. So these are things you want to commit to memory at some point. Maybe, I don't know if this course is the right one, but certainly they need to be in your memory for calculus 2. All right? So how do we prove these things? So I'll show you. And the proof, it's very simple. So here's the idea. Sine of 2 theta is what? Well, that's sine of theta plus theta, right? So use the adding angles formula, right? What do we got? Sine theta cosine theta plus sine theta cosine theta, also known as 2 sine theta cosine theta. So there's that one. So how do you think we're going to get the cosine 2 theta one? Same song and dance, right? So cosine of 2 theta, cosine theta plus theta. So by the adding angles formula for cosine, it's cosine cosine minus sine sine, right? So that is cosine squared theta minus sine squared theta. Now, how do we get to the next thing that's claimed up here? How do you change that to, oh, I think I made a typo. Should this be 1 minus sine squared theta. Does that seem right to you? It actually doesn't seem right to me. Let me show you why. We know cosine squared theta plus sine squared theta is 1, right? So that means that cosine squared theta is what? Cosine squared theta is 1 minus sine squared theta, right? So if you substitute that for cosine squared, we get what? We get 1 minus, not sine squared, but 2 times sine squared theta. And that's important because that 2 goes into deriving this formula down here. That's where that half comes from, actually. Right? So this is equal to 1 minus 2 sine squared theta, which could also be written as 2 cosine squared theta minus 1 by essentially the same bit of algebra. How do you think we get the tangent formula? Tangent 2 theta will be sine 2 theta divided by cosine 2 theta, right? So you got choices. Right? We could do it doesn't matter, right? Any one of them, the algebra will work out the same, right? But so sine 2 theta is 2 sine theta cosine theta. And cosine 2 theta, well, which one do you guys want me to pick? We got like this one or that one. What do you think? I want to use the one with the 1 in it. Well, we've got two. Oh, there's the 2. I guess, man, I can't make up them. I guess I'm going to use the first one, cosine squared theta minus sine squared theta. That seems closest to the formula we're trying to derive. You know? Now, how can I simplify that expression to get tangents? What am I going to do? Looks like, well, I want to get a 1. I'm trying to get a 1 here, right? So I probably should just divide the top and the bottom by cosine squared. That'll probably do it for us. So we got 2 sine theta cosine theta divided by cosine squared theta divided by cosine squared theta divided by cosine squared theta minus sine squared theta divided by sine squared theta. Do you see how that simplifies? So guys, the reason I do proofs in here is because the proofs are actually homework problems. If you look at them, like, seriously, like the steps that we're going through in all these proofs, they're very much the same kind of steps you need to make in your homework, right? So I think it's worth our time. And I also want you to understand that these are things that you can work out for yourself if you want to, you know? So look here. So the cosine squared and the cosine leaves me a sine over cosine, right? And then downstairs I've got 1. And then I've got, well, that's sine over cosine, isn't it? But we could square it, take the square outside. Which is 2 tangent theta divided by 1 minus tangent squared theta. Oh, yeah, I'm sorry. I'm an idiot. Yeah, that was supposed to be cosine squared. I said cosine squared, and I wrote sine squared. Dummy. Me, not you. Right? Now, this is not the only identity that you could find here. I would point out there's also an identity for tangent squared that we can derive. what would the identity be for tangent squared? I'll do it back over here. So let's see here. So that would be sine squared over cosine squared, right? So one nice way to get an identity there would just be to use these two. See, that's 1/2 1 minus cosine 2 theta divided by 1/2 1 plus cosine 2 theta. So here we go. That's just 1 minus the cosine of 2 theta over 1 plus the cosine of 2 theta. And there's kind of a neat identity for tangent squared in terms of cosine 2 theta. So check that out. Cosine squared, sine squared, and tangent squared are all specified by knowing the value of cosine 2 theta. It's kind of funny. Let me show you an example with some numbers. All right. So kind of take a break from our identity proving and look at this one. So suppose we got the triangle 4, 3, and 5, all right? And here's angle theta. Now the question is to find sine 2 theta, cosine 2 theta, and tangent 2 theta for this triangle. Well, not for the triangle, but for the related angle of 2 theta, right? The triangle has angle theta in it. So how do we do this? Well, it's not too hard given what we have in front of us, right? So like first order of business, if this is the triangle, what are cosine, sine, and tangent? Cosine theta adjacent over hypotenuse, right? So 4/5. Sine theta, what's that? 3/5. Tangent. 3/4. I don't know if we'll need all those, but there they are, right? Okay, so we got that. Now we're trying to find sine 2 theta. How's sine 2 theta work? Sine of 2 theta is 2 sine theta cosine theta, right? We just worked it out. So plug it in. We've got 2 times 3/5 times 4/5. So what's that work out to? Excuse me. I believe that is 24 over 25. So there you go, 1 down, 2 to go. How about cosine 2 theta? You got choices. We could use any one of these, right? Well, let's use the last one. It's 2 cosine squared theta minus 1. So that's twice 4/5 squared minus 1. So 4 squared is 16. 16 times 2 is 32. So I've got 32 minus 25 over 25. So I converted the minus 1 into 25 over 25 because I wanted to make a common denominator because, well, fractions. And so 32 minus 25 is 7 over 25. There you go. That is cosine 2 theta, right? Now, you guys could have solved this problem before we had these identities, right? There's a path. What could you have done? You could have taken the triangle, find the, exactly, just find the theta, double it, and then you could have calculated these things with your calculator. Yeah, probably. probably would be quicker if you thought of it. Let's see here. But we are showcasing the identities right now, so let me continue. So tangent 2 theta is 2 tangent theta. But there's, you know, more than one way to skin a cat, but no matter how you slice it, like the end is what we want, right? Because cats are evil. But twice times 3/4. At some point, these comments are going to get me in trouble. 1 minus, I've not yet had a diehard enough cat lover to like chastise me for these spurious, violent cats towards violent cat comments. Anyway, so 9/16 is 3/4 squared, right? And so if you multiply this by 16 over 16, you get 2 times 3 times 4, which is 24, over 16 minus 9. So I believe, and oh, I'm being really, really dumb here. What would have been an easier way to get 24/7? This is also what? Sine 2 theta over cosine 2 theta? Like, duh. That would have been like way, way easier. The 25s cancel. So I think one of the lessons of trigonometry is that you can always make a problem harder than it needs to be. Like, there are so many paths to follow, right? Let's look at another application of the cosine squared identity. And the thing I'm about to show you is something you'll need to do in calculus too. This comes up. So I think this is a good exercise for us. Let's expand cosine to the 4th power of theta. Cosine to the 4th power of theta. So we should look at that as cosine squared theta times cosine squared theta, right? That's what cosine to the 4th is. It's cosine squared times cosine squared. So what is cosine squared times cosine squared? Well, we have identities for those, right? Remember that that's 1/2 1 plus cosine 2 theta times 1/2 1 plus cosine 2 theta. So you can take the half times a half and it gives you a quarter. We'll keep that out front. And then we multiply it out. We got ourselves a 1 plus 2 cosine 2 theta plus cosine squared 2 theta. Right? Now, there's really nothing more I can do with the first 2 terms. They are what they are. But the last term, we can pick on that, right? And I'll use another letter just to try to emphasize what's going on here. We can look at this as cosine squared beta, which is 1/2 1 plus cosine of 2 beta, right? But here beta is 2 theta. So what does that mean? Well, 2 beta is going to give us 2 times 2 theta, which is 4 theta. So what do we have? We have this. I'll make these square so you can see them better. Right? Now we can collect the 1 and the 1/2. That gives us 3 halves, right? And then one last thing here, 3/8 plus 1/2 cosine theta plus 1/8 cosine of 4 theta. And there you go. We have expanded cosine to the 4th of theta as a sum of a constant cosine of theta and a cosine of 4 theta. These kind of calculations are possible for any power of sine or cosine. You can expand them as a sum of sines or cosines of lesser of multiples of the argument, something like this up to the power. And the way this is done is through the application of the sine squared and the cosine squared identities I showed you. But anyway, I have a secret to tell you. Everything we're doing right now, there's one overarching universal algebraic method to solve all of them. But I can't tell you yet. I'll tell you eventually, though. You'll see. Anyway, that's all for today. Well, we need to work through it the standard way before I